Okay, I promised you there would be a backward Euler method, and that's what we're going to do today. So in the backward Euler method, it's called that because you kind of work backwards from the next point. Another way of putting it is that it's an implicit method where you have to solve for the particular y value you want. So what we do is we say, look, we're looking for y sub k plus 1. So we start with y sub k, we multiply h times the value of f, but we want to evaluate f at the next point, at xk plus 1, yk plus 1. So this means we have an equation that we have to solve for y sub k plus 1. So, let's see, so, right, this variable occurs in two places, so that's what we have to solve for. And that means that we're going to have to use some kind of root finding method, right? Some kind of root finding algorithm will be necessary in order to solve for y sub k plus 1. Now, it's worth pointing out that this isn't exactly the best estimate for the derivative either, right? What we would really like to multiply by, if we could, is the average value of f between xk and xk plus 1. Well, this isn't necessarily going to be the average value, so in a way this seems like it's just as bad an estimate as the one using the Euler-Forward method, where we just evaluated at xk and yk, right, just at the previous point. However, this has other advantages which I'll explain, but they're not obvious, I think, when you first look at those. First of all, just to explain the difference between the two methods, Euler-Forward and Euler-Backward, suppose we're working with an ODE in which f sub y is positive, right, so that the f is increasing in the second variable, in the y variable. In that case, then you would expect that the true solution over here, right here, that the true solution is the black line. It would be concave up, right? Because the derivative of y prime. Note that in this case, f sub y indicates what the second derivative of y would be, right? Because f represents y prime, so f sub y would be kind of indicating what the second derivative of y would be. So since that's positive, we would expect this to be concave up. Now, in the Euler-Forward method, what we do is we look at this point here, and we calculate f at this point, and suppose that the blue line here represents the value of f at the current point, or the previous point, right, the point that we've already calculated. Now, because we're assuming that f sub y is positive, that means as we move up along this line, we expect the slope would actually get greater, and that therefore this blue line is going to be an underestimate of the true value, right, as you can see here. The slope at this point was lower than the average slope along the curve, so the Euler-Forward method will give us an underestimate for the value of the true value of the function at x sub n plus 1. On the other hand, the Euler-Forward method is based on getting the slope at the new point, right? Choosing a new point here so that when you calculate the slope from the old point to the new point, it comes out to be the value given by f at the new point, right? So because f sub y is positive, we would expect the slope calculated at the new point, which is going to be at a bigger y value, is going to be the value of f will also be bigger, and therefore the slope will be steeper at this point, and therefore what you'd get here is that the Euler-Backward method will give you an overestimate, a higher estimate than the true value of f, right? So in a situation like this, where f sub y is positive, the Euler-Forward method will give you an underestimate, and the Euler-Backward method will actually give you an overestimate for the true value of f. And then, of course, things will be reversed if this is if f sub y is negative, right? However, again, it's still not obvious why the Euler-Backward method, or in what sense, if any, the Euler-Backward method would be preferable to the Euler-forward method, right? So let me try to explain under what circumstances it actually is better. Now, there's this concept of absolute stability on page 395 in the textbook. It's a very strong condition. I don't want to get into the actual mathematical details of it, but loosely what it says is that the error in yk does not get worse as n. I should have said, that should have been an n there. Sorry. I should have said the error in y sub n does not get worse as n increases. In other words, as you iterate and go from k to k plus 1 to k plus 2, right? Y sub k plus 1, y sub k plus 2, that the error does not get worse over time. Now, you might think that's pretty unlikely, and yeah, it kind of is. There's going to be propagated error that you inherit from the previous y sub k, and then you're going to be adding truncation error at each step. So it seems like a very likely, this is kind of a hopeless request for the error to actually not increase over time. However, this apparently very strong condition can be satisfied if the ODE is well conditioned. And remember, ODE is well conditioned if f sub y is less than or equal to 0. Remember, I talked about this in a previous video. I said that in this condition, you kind of get a negative feedback loop where the error tends to result in a smaller error next time, right? The further you are off for y sub k, then that's going to have a self-correcting effect for y sub k plus 1. So this isn't actually a hopeless condition. Absolute stability, as strong as it sounds, it actually can be satisfied with when the ODE is well conditioned. So you can have a kind of a self-correcting ODE, right? Where if an error develops because of this condition, that f sub y is less than or equal to 0, the error may actually get smaller in the future. So again, loosely, what we're going to want to be checking is the error at stage n plus 1, is it compared to the error at stage n, is it no bigger, right? So we'd like to see that if this inequality can be satisfied, that the absolute value of the error at n plus 1 is divided by the error at n is no greater than 1, right? So the error is not increasing. Okay, so what we have to do is we have to find a way to estimate this. Now, we can actually do this. Let me first take a look at the forward Euler formula over here. Now remember that we actually came up with the asymptotic error for the forward Euler formula. We came up with this formula, right? It basically said that En plus 1 equals 1 plus h times f sub y. F sub y has to be evaluated at a particular intermediate point times e sub n, and then there's an extra term that's of order h squared. Okay. Now, in the following calculation, I'm going to ignore the order h squared term, right? I'm going to consider that that's relatively small, right, compared to the other term. Remember, this is the truncation error. It's of order h squared, so I'm going to consider that's relatively small compared to the propagated error, which will be of order h. And so I'm just going to ignore the order h squared term. Then if we take these two terms here, right, and just divide by En on both sides, we get this. So the ratio of En plus 1 to En is equal to 1 plus h times fy. And again, we're evaluating fy at some intermediate point. I didn't feel like rewriting those details about exactly where fy was reevaluated, but we're assuming that h is reasonably small, so fy isn't going to vary too much. And then we want this ratio, right, the new error divided by the old error, we want the absolute value of that to be less than or equal to 1. Now, this is an easy thing to solve. If you want this inequality satisfied, then, well, first of all, keep in mind that h is positive, right? And so the only way this can be satisfied is if fy is negative. So that's one condition. Fy has to be less than 0, or less than equal to 0, I guess I should say. It's okay if it's equal to 0. On the other hand, it's conceivable that fy could be too negative. That is, if fy is too small, too strongly negative, then the value of this could actually, ooh, I did it again. The value of this quantity here can actually be less than -1, in which case this inequality would be violated. So the condition, second condition on fy is that fy has to be greater than or equal to, I should have said, -2/h, and then this will be satisfied. So with the Euler-forward method, we can see that absolute stability can be achieved if fy is in this interval. You could also think of this as a condition on h rather than a condition on fy. Depends on how you want to think of it. But the point is, it is possible for this absolute stability condition to be satisfied using the Euler formula, the forward Euler method, right? However, well-conditioning by itself is not sufficient for this. Well-conditioning just says that fy is non-positive, right, less than or equal to 0, but well-conditioning does not include this second condition that fy should not be too negative. So, if you're using the forward Euler method, then we can say that let's see, let me get rid of some of these boxes. Then we can say that well-conditioning is not sufficient. It's necessary, but it's not sufficient because it only says that this is true, and it doesn't include the second condition. Okay, now let's look at the situation with the backwards Euler formula. So what I have to do here is I have to quickly and easily derive the asymptotic error formula for the backwards Euler. So I'm going to use some shortcuts here. I'm going to do a little hand waving. But remember, the basic formula for the backwards Euler is this. I just copied this from the first slide. We want to solve the equation y sub k plus 1 equals y sub k plus h times f, and f is evaluated at the new point, x sub k plus 1, y sub k plus 1. So that means because this y sub k plus 1 occurs in two places, this equation implicitly defines y sub k plus 1. And if you think back on calculus, I think they do this in M310. They talk about implicit functions and implicit differentiation. Well, this will be a kind of a nice, simple exercise in implicit differentiation. We can think of this equation as defining y sub k plus 1 as a function of y sub k. If we know what y sub k is, then that essentially determines what y sub k plus 1 will be via the solution of this equation. We have to solve this equation. Now, we may not be able to solve this equation explicitly. However, by thinking of y sub k as some function, I'll call it g, some function of y sub k, we can at least differentiate this equation implicitly and solve for g prime that way. So we can find out what g prime is. So let's see. So if you do that, if you differentiate y sub k with respect to k, that's just the derivative of g, right? G is just y sub k expressed in terms of as a function of y sub k. So differentiating the left side gives us g prime. On the right side, differentiating y sub k with respect to y sub k just gives us 1. H is a constant, that just goes along for the ride. Now, when we want to differentiate this expression with respect to y sub k plus 1, with respect to y sub k, we note that only the second argument depends on y sub k. The first argument, x sub k plus 1, that is always going to be the same regardless of what the y values are. So this term depends on y sub k only through its second argument, and therefore to differentiate this factor with respect to y sub k, we take the derivative of f with respect to its second argument, which is f sub y, evaluated at the same point, and then multiply by the derivative of y sub k plus 1, which, as we saw, is g prime. So we get this expression, this equation in g prime, and now this is just a linear equation. We can solve this for g prime. right? So we find out that g prime is equal to 1 over 1 minus h times f sub y. Now, this will allow us to get a kind of asymptotic error formula, because this tells us how this will tell us how the propagated error behaves. This says that if you have a slight error in f sub y, this shows you how the error will be propagated onto the next term, right? So, in other words, y sub k, how does that vary depending on what error you might have in yk? Well, what we do is, essentially, we're going to think of it in terms of this equation. Y sub k, we're thinking, is a function, sorry, y sub k plus 1 is a function of y sub k. A small error in y sub k will produce a corresponding propagated error in y sub k plus 1, and that error is approximately equal to the derivative g prime times the error in y sub k. So in other words, this is, again, playing the role of like delta y. This is like the error in yk, and we multiply that by the derivative. So delta yk times the derivative gives us an estimate for the error in y sub k plus 1. Now that'll be, you know, it's only an approximation. It'll be accurate up to like a second order term in h. Okay? And again, we're kind of, in this calculation, we're kind of ignoring these second order terms. So let's just focus on this equation now. And again, we can solve for the ratio e sub n plus 1 over e sub n, take the absolute value, and it becomes this inequality. We want 1 over 1 minus h times fy, absolute value, to be less than or equal to 1. And you'll see this is satisfied automatically as long as fy is negative. As long as fy is negative, then this denominator will be bigger than 1, and therefore the fraction will have a value less than 1. So the only condition on the backwards Euler algorithm for absolute stability is that f sub y be less than 0, which of course is exactly the same as that the ODE be well conditioned. So the good news is, if you're using the backwards Euler algorithm, then well conditioning is sufficient for absolute stability. Okay, then you can be sure that the solution will not become more inaccurate over time. That is, as the solution develops, as you go from y sub k to y sub k plus 1 to y sub k plus 2, right? As you iterate, that the error will not get worse over time, as long as the ODE is well conditioned. Okay. Now, for practical purposes, I mean, having just gone through a long song and dance about treating y sub k as an implicit function of, y sub k plus 1 as an implicit function of y sub k. In practice, we don't really want to try to solve that equation exactly, right? So in practice, we don't really want to try to solve this equation for y sub k plus 1 exactly. So what are the alternatives? Well, we can estimate it. There are various ways to estimate it. It turns out, apparently based on years of experience by people who do this for a living, that it seems to be adequate if you simply start with an initial guess that, let's say, by the way, r here stands for the root. So r, if we get the exact value of the root, then r will be equal to y sub k plus 1, right? So r is the root in this equation over here, right? And we use an iterative method where we start off where our initial value for r is simply equal to the previous value of y sub n. And then we say, look, we'll iterate it, and we'll say the next value of r will be equal to the value we get by plugging in the previous value of r into the formula, right? So we have an initial estimate, we plug in that estimate for the root, we calculate the value of y sub k plus 1 based on that, and we get a new estimate. And it turns out, in practice, it seems that you only have to do this about twice. You only have to iterate about twice until you get a reasonably good estimate. It helps if h is small. Now, I should warn you. I say that if h is sufficiently small. However, remember, in this process, we're solving an ODE. That means one of the things we're doing is we're trying to estimate derivatives, right? An ODE is an expression for y prime, for the derivative. And remember that numerical approximation of derivatives is actually more problematic than estimating integrals. And in particular, making h smaller is not always helpful when you're estimating derivatives. So you cannot make h as small in problems like this as you could in simple problems of estimating integrals, right? If you're just estimating an integral, you can make h smaller and smaller, close to the limit of what the machine can handle, and you'll get better results. But that's not true when you're evaluating or estimating derivatives, or when you're working on differential equations. You cannot assume that h is close to the machine limit of what small numbers what small numbers can be represented on the computer. Okay, but nevertheless, this, as I said, in practice, it seems to work pretty well. Writing the whole thing out, we can actually, since we're only iterating this twice, we can actually write the whole formula out in practice for what y sub n plus 1 will be. It'll be y sub n. Well, I'll tell you what, let me start from the right side. We start with our initial estimate, which is y sub n. We use that we iterate that once to get the first iteration, y sub n plus 1 plus h times f sub x n plus 1 comma yn. That's our first iteration. That's an updated estimate for y sub n plus 1. But then we iterate one more time. We plug that in for y and evaluate that expression one more time, and we get the second iteration, and that's the estimate that we go with. So an upside of this is that you can write out the whole formula in a single line, and you don't have to use a for loop, for example, to code this up. Okay, now in a very similar vein, there's something called the trapezoidal method, and this corresponds to the trapezoidal method for estimating integrals. Finally, we're going to use what we learned about estimating derivatives. Remember, what we finally learned in estimating derivatives is that the best estimate to use is if you want to estimate a derivative g prime, you take g of x plus h minus g of x minus h divided by 2h. So in other words, you take a point on the right and a point on the left, and you take the slope between those two, and that gives you the best estimate for the slope at the midpoint x. Right? So then there's a natural way to apply that here. What we do is we try to say that an estimate for the average slope from xn to xn plus 1 would probably be the slope at a point halfway between them, and that would be approximately given by this formula, right? If you take the value of the slope at xn and the value at xn plus 1 divided by 2, what you're getting is essentially the value of the slope at a point halfway between them, and that should be a good estimate of the average slope between xn and xn plus 1. So this seems like actually the best way to go, right? We want to pick a point or value y sub n plus 1 such that the average slope from xn to xn plus 1 would be given by this formula, right? And that means, once again, we have to solve an equation implicitly. We want yn plus 1 to be equal to yn plus h times the average slope between those 2 points. And we're using this estimate of the average slope, but that means, again, y sub n plus 1 occurs in 2 places on both sides of the equation. So this is, again, an implicit method that where we have to solve for yn plus 1. Now again, you can do this by iteration, and again it may only require a few iterations to get a good estimate. As it happens, the code that Atkinson gave for doing this, he actually tries to he uses the iteration method in order to solve this equation. That is, he starts with an initial estimate that yn plus 1 is just equal to yn, and then he iterates again. But in the code he wrote, he actually iterates up to 10 times. So this is the trapezoidal function. It's a trapezoidal MATLAB function. Again, it's similar. The inputs are similar to the Euler 4 function. You give it the initial x value, the initial y value. You give it the right endpoint for x. You give it the h, right? The h, the intervals between x values. You give it the function, but there's one extra argument at the end, which is the tolerance. That is, how accurately do you want this equation to be solved at every step of the way? So as I said, he will in his code, he will iterate the approximations up to 10 times. If he doesn't get within the tolerance required in that time, I think he reports an error. Yeah, or no. Well, he reports that it was not converging after 10 steps, and then I think he continues with the calculation, but just warns you that the root finding method did not quite succeed. Okay, so there might be some error in that particular root. Let's see, anything worth pointing out here? Oh yeah, let me just go through the loop here. So what he says is well, the way he does it, he says, look, our initial estimate for what, let me try this. Our initial estimate for the new y value, yt1, will be the old y value, y at the previous index, right? So I represents the time element, if you like, the successive x values that you're looking at, right? So this says take the previous y value plus h times fyt. Fyt is exactly the function f evaluated at the previous point, right? So so he uses that to get the first iteration, and then he goes through a loop. He says while the difference is greater than the tolerance and the count is less than 10. Like I said, he's willing to do up to 10 iterations in order to try to find a solution. And he'll break the loop as soon as the tolerance is less, sorry, as soon as the actual difference, the error in the equation is less than or equal to the given tolerance, right? And he says that, look, y sub, and then he iterates it each time, right? So now he says the new estimate is going to be equal to, again, the previous y value plus h times, and then what he does is he takes the value of the slope at the previous point and the value of f at the new point, and he averages them, divides by 2, right? And then he calculates the new difference, right? The difference between successive values of the approximation. Then he exchanges the two values. The old one becomes the new one, and then the new one is free to be updated on the next time around the loop, and he updates the count. Okay, so it's very similar to the root finding algorithm we used back at the beginning of the semester, right? Just iterating and checking to see when the difference between successive approximations is below the tolerance, right? And this method, if you use this trapezoidal method, This is the best of the three we've looked at so far. Turns out the convergence is of order 2. That is, if you use the trapezoid method, it actually cuts down the truncation error, because trapezoid is a much better approximation of the, for the Riemann sum. If you're taking the area of a small slice of the function, then using the trapezoid method gives you a much smaller truncation error, an order smaller truncation error. So it turns out the truncation error itself with the trapezoid method is of order 3. And I mentioned earlier that if the truncation error is of a certain order, then the overall error will be of an order 1 degree less. So the error in the trapezoid method is actually of h squared. So it'll converge significantly more rapidly than the Euler formulas, either one. Okay, let me try this out on MATLAB, and I'll compare the trapezoidal method with the Euler, forward Euler, which was the two extremes of the cases we've looked at. Okay, so first, I'll do the same ODE I was doing the other day. So let's see, yeah, that one, right? Let me first of all do it using the forward Euler method with a couple different h values, so we can compare that with the trapezoidal method. So let's see, xy equals, I want to do, how about, no, this one, how about that? So I'll do it, we'll go from 0 on the x-axis with an initial y value of 1, and we'll go up to 6 on the x-axis. We'll use an h value, relatively crude h value, just 0.1, and using our function f, right, to define the differential equation. Okay, so we'll plot that, plot xy, we get this. Let me make this bigger. Okay. Now let's try it with the same, first of all, let me put a hold on. So let me hold the picture so I can just write over it. Let's change the h value to 10 times smaller. So this should give us a much more accurate picture, right? So remember that in the Euler method, the error in the solution is proportional to h. So if we make h 10 times smaller, there should be 10 times less error. The error should also be 10 times smaller. So this should be a much more accurate version of the solution. Let's see. Okay, so you can see the difference. Let's zoom in. Right, so the original one was the blue one. Or I should talk. The one with h equal to 0.1 was the blue one. The one with h equal to 0.01 is the orange one here. The orange one is the more accurate one. Now let's see what happens if we try it with the trapezoidal method. Let's see, I think I did that. There we go. Yeah, let's try this one. So we're doing the same range, of course. I'm doing it with the crude h value of 0.1. And the trapezoidal function takes an extra input at the end. You have to give it the tolerance for the implicit equation that you're solving. So I'll set the tolerance, again, pretty crudely, the same as h, it's just 0.1. And let's see what happens. Let's see, let's plot that. This is interesting. So it seems that the trapezoidal method, even with those crude settings, right, with h equal to 0.1 and the tolerance equal to 0.1, this seems to be a much more accurate, well, significantly more accurate solution than even the Euler solution when we used h equal to 0.01. Because it seems that this is going in the right direction, right? Remember I said that this one would be more accurate than the blue one, right? The red one would be more accurate than the blue one. So it seems that following the progression, if we were to use something like Richardson's extrapolation, we'd find that the true solution is closer to the yellow line. right? So in fact, the trapezoidal method does seem to give us a much better result. It seems to give us a result that we wouldn't get using the Euler method unless we used a much smaller h value, right? Interesting maybe to compare, let's see, what kind of h value, let's try the Euler method and go even one order of magnitude smaller in the h value and see what happens. Let's see. Oh wow, yeah. So as you can see, this purple line, that's the Euler method with h set to 0.001, and it's getting closer to the trapezoidal method, but it's not there yet, right? Let me do the same thing. Let's try it with the trapezoidal method. I'm having way too much fun doing this, I know. But let me just try the trapezoidal method one more time, and I'll set both h and the tolerance down to a finer level. And let's see. Okay, so maybe the purple line and the green line, they seem to be largely agreeing with one another, right? So it seems that maybe what we could say is that it seems like the trapezoidal method is kind of equivalent to the, well, it gives us a solution that's comparable to the Euler method, but with an h value that's 10 times larger, right? So that gives you some idea of the difference in power between the two methods. Of course, with the particular function we're using here, we did do up to 10 iterations in order to solve the implicit equation. And so we may not be entirely gaining numerical efficiency because of that, but it does show that the trapezoidal method does seem to give more accurate results, at least with larger h values. Okay, in the next video I'm going to talk about some other methods that can be used. There's, as you can imagine, mathematicians have been working on this stuff for centuries, literally centuries. There's lots and lots and lots of methods for solving differential equations, and since computers have become a thing, computers have been used to solve them, and there's lots and lots and lots of computer numerical methods to solve differential equations. So I will mention some of the other methods that are used currently in the next video.